Hello everyone, we from Group 8 consists of me, MUHAMAD, FAKHRY, ALIMAN, ZAFRAN and CHENG will be present about the airflow in the turbocharger. First, we throw about the background of the topic. Computational fluid dynamics simulation is a computer-based technique for modeling fluid flow and related phenomena. It involves solving mathematical equations to predict and visualize fluid behavior in engineering and scientific application. For Euler method, in CFD, the Euler method discretizes a fixed grid in the simulation domain to track fluid properties at specific points over time. It's suitable for analyzing bulk fluid behavior in pipes, channel, or around jets. The next Lagrange method in CFD tracks the individual fluid particle as they move through the simulation domain, focusing on particle trajectories and interaction. It's useful for studying particle-laden flows and scenarios where individual particle motion is crucial. In this problem statement, we will discuss about how between Lagrangian and linear method can lead to different results in the analysis of airflow in the turbocharger. For Euler method, for macroscopic view, it provides a global perspective on the fluid flow. Next, grid-based analysis. It efficiently stimulates the entire turbocharger system. Computational efficiency, generally faster for overall system analysis. Next, for the Lagrange method, the particle technique, it captures the detailed particle trajectories and local interactions. For macroscopic insight, useful for studying turbulence, dispersion, and specific flow patterns. And transient effects, it well suited for capturing transient and complex interaction. For combined approach, for hybrid simulation, it combines Euler for global aspect and Lagrangian for local details. And comprehensive understanding, it achieves a balance between global performance and local effect. For consideration, computational cost, Euler is more accuracy and Euler is more efficient. And Lagrangian can be computationally intensive. For accuracy versus detail, trade-off between accuracy and computational cost. For selection basis, depends on the analysis goal, level of detail needed, and available computational resources.
Hello everyone, my name is CHENG and my metric number is ES04492. I will introduce objectives. The first is microscopic understanding, using Euler methods to gain a complete understanding of fluid behavior. The second is a microscopic analysis using Lagrange methods for detailed example tracking and interactions. The third is parameter extraction, extracting key parameters for comparison. The last one is the method comparison, identifying the different contributions of each method to turbocharger aerodynamics.
Okay, hi everyone, my name is ZAFRAN and my metric number is 2395. So now I will explain on the methodology of the simulation. Okay, so for this simulation, we have chosen to use ANSYS software to do the simulation. So in the ANSYS, we have several steps that we have to follow before the simulation can be done. So the first one is the turbocharger modeling. So for the model, we have decided to import a model of a turbocharger. So from the model, we have created a mesh on the model. So the finer the grid, the more accurate the results. And also, we have to define the initial parameters. So the initial parameters includes the density of air and viscosity. And also we have to set the boundary conditions. So the boundary conditions is whether we want to make it as a steady flow or we have turbulence inside the turbocharger. And next, we have to choose what approach we want to do. So since we are trying to compare between Eulerian and Lagrange method, so we have chosen the cell method, which is coupled Eulerian Lagrange. So this method will solve the Navier-Stokes equation to solve for the Eulerian, and then the software will track the movement of particles. So that would solve the Lagrange method. Okay, so then we will do the data analysis. So we will observe the fluid flow path and the particle movement, and from that we will compare the difference in the result from the Euler and Lagrange method. So as we can see from the video, so this is the simulation video that we have done. So from this simulation, we have two questions to be solved. So the first one is, how does Euler and Lagrange method differs? So Euler method will solve for the fluid dynamics of a certain area in a control volume. So in this case, the lines that you see inside here is are actually solving for the Eulerian method, whereas the individual spherical shaped object is the particles, which will solve for the Lagrangian method. So Lagrangian method is more in-depth study of the fluid simulation. So it will focus on the behavior and movement of each individual particles of the fluid. So how do we interpret the results? So from the result, there are actually several key informations that we can extract. But however, in our case study, we are more interested to only see the visual output. So we can compare it visually. So as I mentioned, the lines are the Eulerian method and the spherical is the Lagrangian method.
This study emphasized Euler efficiency in capturing macroscopic change within turbocharger, where the Lagrangian method excels in macroscopic detail, tracking individual particle behavior. Comparing simulations, Euler focused on particle concentration in specified regions, while Lagrangian offers a nuanced understanding of particle distribution and behavior throughout the system. This disparity underscores the necessity of selecting the suitable simulation method to enhance comprehension of turbocharger fluid dynamics.